So thank you very much for being here. And we have a really exciting venue coming up today. We have 3 presentations from 3 undergrads. The first presentation will be from Stone, and he will be presenting his work on crowdsourcing in data science and machine learning. The second presentation will be from Sachinda, and he will be presenting his work on computer vision for music. And third, the last presentation, I will actually be presenting my work on interpretability robustness for neural networks. So if you haven't seen the flyer yet, it's available in the announcements channel. And you'll get basically the same schedule, and you can also read the descriptions on the same flyer of each presentation. So the structure of this event will be each person will give their presentation, and at the end of their presentation, they may choose to also allow for a Q&A for their presentation. And feel free to unmute or use the chat to ask anyone any questions at any time. We will also have a general Q&A at the end. And the general Q&A is, the purpose of it is largely for if you have questions that you want to ask all of us, all the presenters, questions like, how did you get involved in research? What's your favorite part of research? What's it like working with so-and-so professor? Stuff like that. Feel free to ask us in the general Q&A. I don't mind you also asking me during my Q&A section at the end of my presentation. You know, the other presenters, you know, it might vary. So yeah, so yeah, again, I'm very excited, and thank you again for coming. And if you're watching this on YouTube after we've recorded and posted this, thank you also for watching, and we hope you enjoy. So it's 4:06, and it looks like we have a good amount of people here. So why don't we go ahead and start a little early? We'll have our first presenter, Stone, share his screen and start his presentation. So I'm going to stop sharing my screen, and I'll let Stone take over.
Do you guys see the screen? I have no idea what's being shown right now.
Yeah, we can see it.
You can see the slides, right? Okay, cool. Feel free to ask questions in the Zoom chat. I'll be here and looking around. Okay, yeah. So I'll begin presenting. So today I'm going to be presenting basically a concept known as crowd ML, or getting humans in the loop. So if you don't know what a crowd means, a crowd is like people. It's just groups of people working together or separately to do some task. ML, machine learning, you guys have heard of the term. And humans in the loop is something I'll also talk about. So this is work between me and Brian McInnis, a postdoc at ProtoLab under the general design lab department. So here's a short agenda for what I will be talking about today. So I'll first introduce a simple background of what crowd ML is and what humans in the loop means and some of the current literature surrounding that. I'll also dive into what issues these frameworks are trying to tackle and some of the relevant literature that exists so far. I'll also get into details of how we, me and Brian, are trying to tackle this integrated approach using decision tree models. I'll go into some deeper details about decision trees. So if you don't know what decision trees are or some of the more advanced methods regarding them, I'll explain them out. And then I'll talk about how we plan to approach the task of making a generic, fully automated system like decision trees, linear regressions, logistic regressions, mixed effects models. I don't know, there's a ton of different models, even neural networks even, become an integrated crowd machine hybrid system. And then maybe I'll talk a bit about potential future plans we have. Just a note, this is still very early stage in our research. We literally only just finished our abstract and we're still designing a couple things. So first thing. So first, a quick background on what modern day crowd working looks like or crowdsource looks like. So modern day ML pipelines, if there's going to be any kind of crowd workers involved, usually the only purpose of a crowd worker is to label data or interpret model results and determine the error. Crowd workers right now are typically reserved to performing simple tasks and they don't communicate with each other with doing so. And this raises a number of issues. This is prone to erroneous or unstable labeling at times, and different workers can create mismatching distributions of the labeling. For example, let's say we wanted a crowd worker, we want to crowdsource the rating of Wikipedia article content so we can train a neural network model to predict how good a Wikipedia article is. When rating Wikipedia article content, some workers might give above average ratings, some might tend to be more strict, and you can see how this can spiral down to a lot of different issues. Typically, people use basically Amazon's Mechanical Turk, which is like an online platform to get crowdsourcing. Usually, you'll pay the crowd workers some amount of money for each task, and they'll just work on a task. There's a couple other platforms. I think there's one called Crowded as well. But yeah. Oops, next slide. So what is crowd ML? In my opinion, I don't think crowd ML has been well defined yet. And if it's really defined, crowd workers are typically reserved to either end of the model, not in the middle. Simply put, it's basically it's just an intersection of machine learning and crowdsourcing or crowd work. Somehow we want to involve crowd workers, humans, into the machine learning pipeline. For maximum benefits, my group is proposing that we can gain a lot more from crowdsourcing, and the hybrid relationship between the crowd and ML models. We can get a lot more than just separating them and stacking them one on top of another. So yeah, so here's the first main concept. So what are humans in the loop? So here's a nice article by Stanford on what humans in the loop is and how people are designing interactive AI systems nowadays. The graphic on the right kind of just shows what it is kind of in general. So usually we have an AI subsystem. It will make some prediction, and then the human in the loop will then help the AI subsystem refine their decision and refine the model iteratively. So in this sense, we're basically treating AI as a tool, not as the absolute ground truth decision maker. Where it's often used. Right now in modern day, AI systems are quite entwined in our lives. You can see AI systems being used for credit fraud detection, resource allocation in federal, in different states. So for example, if you're allocating federal funds for the schools, typically they might use some kind of model, whether it's machine learned or not. There's many models like this. But the point of humans in the loop is that it's supposed to help us take a step away from perfect intelligence machines, which exhibit a lot of issues. And I'll talk about that a little bit later. HITL, human in the loop, can help improve transparency, incorporate human intelligence, and enable much, much more powerful systems. And you can understand how we incorporate human intelligence. Human intelligence in this framework kind of just refers to things that humans can do. For example, humans have the ability to be creative, to be thoughtful and evaluative, whereas AI systems and models in general are quite restricted in terms of what they can do. Although I do want to argue there's a lot of recent research now into how AI models, especially reinforcement learning models, can learn surprise and creativity, but that's very early stages and at the moment, not a good substitute for humans. Another really important thing is transparency. I'll talk about why transparency is so important in a moment, but this is actually also one of the issues we try to tackle. But what we'll notice is that typically in a lot of modern day production pipelines, we have two issues. We have something called algorithmic aversion and automation bias. So what are these two terms? So algorithm aversion is when we have some system that is some algorithm that's producing predictions. And the humans who are using those predictions tend to not use the model. So they are undercompliant of the model. There's undercompliance. So when will this, why would they not use a model? Well, one of the biggest issues for this is one, they don't have belief or trust in the model, and trust stems from transparency. So if the model is more transparent, e.g. you understood why it makes some predictions, e.g. Let's say we're doing email spam filtering, and let's say the reason why it filters out the emails because it's too short. It thinks it's spam because it's too short. In that case, then the human can then make their evaluation. Should I use the result or should I not use the result? And why should I not do it? As opposed to just making a guess and just guessing whether or not the subsystem was working correctly or not. Another thing is automation bias. So there are times when this is the other end of the spectrum where people will have this algorithm in hand, but will always rely on the algorithm. And this can be an issue, especially in very high risk scenarios where you cannot afford to make mistakes. And also in more ethical scenarios where it's a very political charge or like ethical issue. For example, you're trying to predict something regarding race. This is a very precarious situation because you don't want to get that wrong. Another thing could be determining, I don't know, let's say determining if you're a felon or not. And especially in job hiring systems, just ruling out people just because they're a felon or maybe ruling out people just purely based on their resume has caused a lot of issues. So this is why we want to have a balance between relying on the system and not relying on the system. And to achieve this balance, we propose humans in a loop. All right, that's a little long. So these are kind of main issues that kind of HITL and crowd working is trying to address, where algorithms by themselves typically seem to fall short recently. So first, we need to understand what kind of issues we're trying to address. FAT, or FAT, stands for fairness, accountability, and transparency. In general, without adherence to these three core parts, many systems, especially those entwined with our lives, can pose risks in entrenching existing biases, reducing accountability, and hinder due process. And again, as some examples is predicting or like job resume parsers. They might, I recall there's an article how Amazon's parser tended to rule out women candidates because their algorithm was just biased. Without a human factor in their job resume, like the first part of their resume filtering, you kind of tend to entrench biases caused by your biased data set, such as maybe your data set is full of men only, so it'll only think men are good or some reason. So there are two main ways in which algorithms can be biased and fail to adhere to FAT. One, which is probably the biggest one, the most commonly thought after one, is misrepresented data or just bad data, garbage data. If you've ever taken like COGS 108 or COGS 118A, the professors say the same thing, garbage in, garbage out. And that's still very true. The other thing, which is what we're focusing on, is human error and bias in model design. There's a great article by Vox. If you don't know Vox, it's like a kind of magazine, but they talk about really nice topics. This is part of the Recode series, and they talk about algorithmic bias and discrimination in facial recognition. I highly recommend reading. Yeah. So here's a non-exhaustive list of just human factors that contribute to many typical algorithms on the web. I know this is a little bit hard to read, so you might want to check the slides link. But basically, the process is you start with some information. You do all these just like different information transformations before we finally deliver the final product to the receiver. You'll see that there's technical limitations, there's details about your personal information, there's a human operator, and all these different human elements contribute to potential bias. All these different human elements are typically created by a single human operator, by a single data scientist, or maybe a small group of data scientists who might be out of touch with the actual distribution of data. What I mean by out of touch is like, for example, if you have like 4 random data scientists and they're producing a model for this web system that is trying to parse resumes and filter out resumes. Well, there could be a lot of issues. For one example, if these data scientists have pre-existing biases of what resumes are good and what resumes are not good, those biases will enter the system. Typically, for example, when they're doing feature selection, let's say one of the features you look at is gender, which in my opinion is probably not a good idea. But let's say they include gender for some reason. That can lead to potential biases and it will reflect eventually in the end result, leading to kind of just events such as Amazon's own filtering system causing a lot of issues. But yeah, this diagram is from a paper by called Bias and Algorithmic Filtering and Personalization. Feel free to check the slides, just look at it more in depth. And don't hesitate to ask any questions in chat if anything is confusing or you want to elaborate, or you want to just ask anything about what I've talked about. All right. So why are we focusing on the model instead of the data? Data is hard. We can improve data easily. Collecting data is costly and time consuming. Missing data is a very common issue. And a lot of data interpolation and extrapolation methods fail to capture certain intricacies in the correct distribution of data. For example, 2020 USA Census data hasn't been released yet, but a common expectation right now is because of COVID, a lot of data is missing, and the US Census Bureau right now is actually actively researching methods to handle what's known as something called record imputation, which is filling in missing data. Another issue is just entered data is not always of the highest quality. People who collect data might always enter something wrong. For example, let's say someone is an old grandma. She's aged 97, but for some reason her income level is marked as $500,000 plus. There's probably something wrong because they're probably retired, so they don't have an income. But things like that always happen. David just has asked a question. Can you say that most of these ethical issues are primarily those where an ML model is trying to learn a social construct, e.g. definition of good vs bad candidate, race, gender, etc., which are not well-defined or objective in the first place, in which case attempting to reduce it to an objective formulaic calculations are already an L+ question. Great question from David. A lot of ethical issues are on a fine line. And whether or not you should be even trying to automate that process is a question for debate. In my opinion, I think it's still something that we will have to automate or add some kind of model to try to determine, mostly because there's so much data, you cannot do things case by case at this day and age. Like USA has like 300 million people. We cannot be doing things case by case. So we need a compromise. Right now, some of the certain like automatic models, for let's say like credit fraud detection, suffer from a lot of issues, right? They're poorly designed, maybe they have a lot of existing biases encoded in it. And so this is why we want humans in the loop. So David, when you mentioned that some of these social constructs are not well defined, or it can't be really placed into a formula easily, that's where humans come into play. And I'll talk about this, right? I think in the next slide. So improving the model instead of the data. So we want to build a model with the end user in mind, and we want to keep the model interpretable. And we want to keep the model evaluative. So a good framework for how to evaluate interpretability is proposed by Zachary Lipton in his paper, The Mythos of Model Interpretability. Fun fact, Lipton used to be a UCSD grad student. I think he's now a professor at CMU. And he's researching like just AI and I think something to do with HDSI. I'm not quite sure. But now the question is, how can we prove what often is an auto-generated model? How do we incorporate people in it? So what we propose to do is we want to use decision trees as a starting point. So what's the point of decision trees? Well, it's already been shown successes through a past paper called Flock by Chung et al. Flock is a automated system basically that uses a decision tree and creates a hybrid crowd machine generated decision tree. But what is the point of using DTs? DTs are easily visualizable, easily interpretable, and they make a prime choice for some initial research into how can we integrate crowds into an automated model. And again, this addresses David's question. For a lot of very fine line questions, for example, something to do with race, good candidates versus bad candidates based on resume, this is where we want people to make their decisions. For these one-time decisions where you cannot make a mistake, we want a human reading your resume. We want a human evaluating the final model that's been produced. So what's also good about DTs is that they're flexible and applicable to many, many kinds of tasks. Like a really naive one is like spam filtering. Other ones is like resource allocation, questions or tasks based on classification, classifying maybe what income bracket you might be from. And currently, a lot of crowd ML approaches focus on top-down growing of trees. And we kind of want to propose the same thing, but we also want to propose different angles, including bottom-up pruning, which I'll talk about a little bit later. So next few slides, I'm going to explain a bit about what decision trees are, in case some people here aren't quite familiar with what decision trees are yet. So here's a simple decision tree. This is a decision tree that basically filters spam. The way the decision tree works typically, in a binary sense, is at each node that's not a leaf, we have some decision making. So let's say our email length is greater than or equal to 200 words. We go to the left branch to say that is true. Then our next node, we make a second decision, which is checking how many unique words are in our email. And let's say there isn't enough unique words. Then we go to the right branch, which means false, and we classify not spam. So this is just a very simple decision tree. And basically you can plug in any single email, plug it through the decision tree, and you can determine if it's spam or not spam. And we call that decision trees are typically for classification, but there are also regression trees. And every single leaf node of the decision tree is a final classification. Any questions about this? All right. So let's go through how we might, oh, sorry, I was gonna use this slide to determine how we might go through that. I forgot to say this. But yeah, you can see how you can follow a path from the first part, second decision, and classification. So currently, how are DTs automatically created? If you've ever used them before, you probably use something implemented by like sklearn. They have their own set of decision tree models and random forest models, etc. But these are basically the key steps. The first thing you do is you select training data. This training data, for example, is our email data. This email data is labeled with number of words, number of unique words, and the whether or not they have, like, let's say, .edu or .org in an address. We want to incorporate all these different features. So for example, in our example here, we have 3 different features: length, unique word count, and email sender address. And then we proceed to create the decision tree by an iterative fashion or recursive fashion. Using the next node we're going to look at, we're going to find a split in the data along some feature that best classifies the data or best separation. So for example, let's say we figure out that, actually, I'll explain that a little later. And this can be also a k-way split. So our previous examples show a binary split. We can have like a 3-way split, a 4-way split, depends on our data. And there are many heuristics for this, along with heuristics that even regularize DTs by penalizing complexity. And complexity in this sense being how large the decision tree is. So after we find this good separation, we're going to create the k child nodes, one for each split. And if some criteria is met, e.g. a maximum tree depth, or you can't split the data farther, we stop. And otherwise, we recursively repeat the steps 2 to 4 for all unseen nodes. And this is what's known as a top-down approach, and what it grows the tree. I need to drink water. So I'll take you guys through how to grow a decision tree. So we usually you start off with nothing, and we're going to take all our data and we're going to find some split that best separates our data into spam, not spam, for this email example. So let's say, for example, our feature email length is able to classify spam, not spam really well. Let's say like a 70 to 30% split compared to other features. And it just so happens that at 200 words, this threshold creates the best split for spam, not spam. So now we're going to iteratively look at both the child nodes and look at all the data that's associated with those child nodes. So for example, all the data in the left child node, the left spam node, is all the data or all the emails where the length is greater than 200 words. So let's look at that. So we take that, and now we try to find the next feature split that best works. And for example, let's say the next feature split is a unique word count. And let's say the best threshold happens to be 40. Then we create 2 new child nodes, spam, not spam, the classifications, and this grows our tree. We do the same thing for the right side and keep going until some depth is reached or we're done. In this case, let's say our maximum depth is 2 levels, and we'll stop here. And this is our final decision tree. Any questions about decision trees? Are these features predefined? Yes. So usually in an automatic case, decision trees are data scientists or your researcher or just you, you will find your data, you'll create all the features you want. So select features beforehand, generate features beforehand, plug it into this automatic algorithm. There's many automatic growing algorithms. One of them is like CART. There's something called IPT3 or something. You plug it in, automatically grows a tree. And you can see where there's already issues with that, right? The feature selection stage could be biased by the data scientist, which is where we want to incorporate users actually. And you will also notice how interpretable this model is, right? You can literally read off the English for the decision tree to see how each decision is made. And this is also the motivation for why we want to use decision trees as a first step for understanding how someone can incorporate crowds with a auto-generated model to produce a hybrid model that addresses FAT. All right, so the second part of DTs that are commonly done is refinement. Typically, a refinement procedure is usually some tree pruning algorithm. So you start off with a fully grown tree, and then you start pruning it. You start making it smaller. You want to remove things. You want to help, usually it's used to help improve its generalization. But in the case of crowd ML, sometimes you want to do pruning just to remove erroneous nodes. Like for example, let's say let's say for one reason, as a user, you know that having an email address of .edu or .org really doesn't matter because lots of spam email has that as well. So as a human, you would recognize that and you might take that out yourself. So there's different kind of pruning algorithms. There's something called pessimistic error pruning, something called complexity error pruning, which is kind of regularization. You're pruning and you're accounting for the complexity of the model at the same time. Flock, which I introduced earlier, has a refinement procedure that goes top down. So what happens is the user is presented with a machine-generated decision tree. Then the user themselves first chooses leaf nodes they believe should be expanded upon more. And then crowd workers proceed to find potential features to split the leaf node and label new data as necessary. So this answers Jason's question earlier about whether features are predefined. In the classical case without people, yes, they're predefined. But in the cases of crowd ML, like Flock, usually we might have crowd workers finding new features to split the leaf nodes more and label new data as necessary. And then there's a really interesting one. This is a really uncommon thing. I don't think it's popular yet, but I think it's really interesting because it actually matches how humans think better in terms of decision making. So Ignatov et al. They propose a novel tree pruning / growing mechanism known as decision streams. Very confusing at first, but it effectively enables automatic merging of separate subtrees to reduce the size of the tree and improve generalization. So first I'll talk about pruning. So let's say as a user or some algorithm decides that this highlighted node here is bad. It doesn't separate the data well, or maybe it's overfitting a lot by some metric. So all we do is remove it, and now we have this. We remove the node and replace it with a leaf node that's classified with the most common class. And let's say it happens to be spam for some reason. Any questions about pruning? And you can see how this is bottom up. We start from the bottom leaf nodes and we slowly go up to start removing tree nodes. Another thing to note is that when you're pruning, usually if you prune a node, you prune the entire subtree. There are some very specific algorithms that don't do that, but that is typically the case. Okay, next one. This is the more complicated thing. This is what's called a decision stream. And you don't really understand how it works and what's the point of it. But the idea is that when you're using the decision tree, a DT, and you're pruning nodes, you usually prune individual subtrees, or you add to individual subtrees without considering the contextual information stored in other subtrees. So for example, let's say we have two classes, yellow and blue. A decision tree might have some data about the yellow class in the right subtree, and a lot of random data of the blue class in the right subtree mixed in the left subtree. And it's all very messy. It's very big, meaning it's very complex, not generalizable. So we want to make it smaller. So in this case, we're going to do something called merging. We will take a decision stream, we will take the decision tree and merge nodes such that our leaf nodes is smaller in count. And we have less leaf nodes, and that means our tree is actually less complex. And this improves generalization error a lot. It just reduces a lot. And the reason why we were considering decision streams is because it's a lot like how people think. When you're making a decision, right? Let's say we want to determine if we want to bring an umbrella outside today. First thing you might ask is the weather rainy? Is the weather sunny? Is the weather dark? Is it dark outside? Is it cold outside or something? All these different decisions. When you're following a normal DT, you can easily follow a route that's predefined, and you can't access information from the other subtrees. So for example, if you look at the left subtree of the decision tree, it does a good job of getting the blue class, but some of the blue class information is actually stored in the right class. So how do you get that data? Well, in a classical DT, you can't. But if you're a human and you're thinking about it, you actually have this contextual information. So this is kind of motivation for us to think about this new kind of the DT and think about how we can incorporate crowds in that. Any questions? Okay. So where do people come into the frame? So there's a lot of algorithms and automatic feature selection algorithms and tree growing, pruning algorithms that are out there. And our main process so far has been basically, we're going to look at all these different algorithms and we're going to look at how can they be broken down to steps. So recall that I kind of broke down the steps for tree growing. We kind of did this for every single algorithm and analyzed all of them. Oops, I should close Discord. Give me a second. All right. So there's kind of two levels evaluation. The people can have opportunities to help improve a model by looking within the tree or some kind of post hoc analysis. And post hoc analysis being after you're running all the automated algorithms, then you reevaluate the tree and tell the system to like, oh, remove this node or add this node or something. So each opportunity for human evaluation can be categorized into like a global, middle / meso, and local levels of evaluation. For example, a local level will be a post hoc evaluation of individual DT nodes and the decision associated with why that node was created. So for example, let's say one of the splits was unique number of words in email is greater than 40. A human will then come along, look at a decision, and analyze in the contextual sense, is that a good decision to make? And you can imagine there's more complicated decisions and more high stakes scenarios. For example, let's look at resume parsing or filtering. So let's say a decision tree learns from data that could be biased, that gender is a very good indicator of who to hire. But we know that at Amazon that we do not want to have that happen because we know that that's actually not really a thing. It just happens to be our data is skewed. So a human evaluator, a crowd workflow would look at the decision tree together and analyze and realize, no, we can't have that. It doesn't make sense. We know from our experience that filtering resumes by gender is not the way to go. So that would be an example of a local level of evaluation. A global level would be deciding which algorithm or method to apply when growing or pruning a DT. In my opinion, I think we might be changing our definition of what global level is, but this is just an example for now. But you can see how there's like different categories of evaluation. So you can be evaluated at global level, the full tree, middle level, maybe a subtree, and then a really local level of just individual nodes. And the point of involving people is that people have the ability to evaluate, to make decisions, qualitative and good educated decisions before making a mistake. Whereas the problem with models is that they make a mistake first and then they refine themselves. And people will refine themselves first before making a decision. All right. So one of the ways we're trying to kind of figure out how to incorporate crowds is using concepts from crowd writing. So Brian, the person I'm working with, he wrote a great article on crowd writing, which dissected about like 24 different crowd workflow systems. And looking at how these different crowd systems have different design features that enable certain features of a crowd to perform creative tasks like writing. And evaluating a model is no simple task. So the idea is that we can take this framework of creative writing and convert it to a framework of model evaluation, which is a difficult task, requires some kind of creativity and thinking. So some core concepts include scaffolding, audience design, planning, goal setting, and more. And each of these form a core component of a crowd workflow, which will enable a crowd to perform more difficult tasks, such as evaluating a model. We plan to use these concepts to build up a framework of how you would integrate a human into a loop, into a decision tree, particularly. Future plans, no idea, but I think we're planning a submission to the CHI conference, which is a conference on human factors computing. At the moment, we focus only on DTs because there's actually a lot about decision trees to analyze. But I think with enough research and thought, I believe you can probably extend the ideas to more complicated models like high dimensional regressional analysis, even neural nets to some extent. And they can be broken down to improve transparency, which is a key component to enabling crowds to look at them and then analyze them. And like just some ideas I'm throwing out for neural nets, things like saliency maps or attention heat maps for image recognition models could be a potential for a lot of involvement for crowds and humans. But again, this just needs more research. If you don't know what saliency maps are or attention heat maps, are kind of just like saying, oh, what parts of the image are most important for making the prediction. So it's like once a model makes some prediction about an image, let's say it classifies as a cat, we send that kind of prediction back to the network and we look at what parts of the image really contributed to that decision. And then attention heat maps, I don't remember what it was, but I recall that in some models you can kind of analyze which parts. It's a different way of analyzing which parts of the model are most important. Oh, Jason goes into saliency maps. Okay, so Jason can talk about saliency maps in his research later. I don't understand them as well as he does probably, but yeah. That's it for the slides. Anyone have any questions? Thoughts, comments? All right. So David just asked another question. David Glukov. When you say crowd/transparency, do you mean making much? Do you mean making much of these decision trees public, for example? As in that case, there may be a risk in terms of abuse. In other words, someone sending spam may use the decision tree to modify the spam. Oh, are you talking about like white box attacks? Where you know the model beforehand, so you can attack it by inspecting it or something. Assuming that's what you mean, no. So the idea of transparency is that the users of the model, not the end users, can. So sorry, let me rephrase it. You definitely don't want. You don't always want to reveal the full model to everyone because, like for example, there are things called white box attacks. If you reveal the full image recognition model, someone can easily fool it. Just adding a bit of doing something called what's called a fast gradient attack. You can add a bit of noise to your image, and it'll change a prediction of a chicken to an image of a chicken and predicting as a horse or something. In our example, when we're talking about transparency, we're talking about transparency in the sense of the stakeholders or the people who are making the model and using the model to help others. So I guess that is an issue. But the idea is that right now, decision trees are completely automatic. And they can get very deep. And a lot of other models using like neural nets, they're completely black box. So let's say you're an operator who's using these models to help decide on credit fraud. If you don't know how these models work, you're more likely to either enter under compliance or over compliance, or in other words, enter algorithm inversion when you shouldn't be averting the algorithm, or automation bias when you shouldn't be completely relying on the algorithm. So by making these things more transparent, it's a bit more obvious how they work, and you can make a better decision after the model makes their own decision. Maybe another way to say is like in production pipelines, usually like a business ideally should be using a model for an initial prediction, and then people should then evaluate that final decision before giving the user, the client, the final decision. So that way you still hide the model, but the people who are making decisions can make much better decisions. Any other questions? Yes, I feel like I rambled a lot about that question. I can't explain it that well, honestly, but yeah. All right, I think I'm going a little bit over time, so I'm going to hand this off to the next presenter. Yes, and yeah, you have slides here. If any question, and I have to leave unfortunately at 5. So if you have any more questions, ping me in the ACM Discord. I'm Stone. You can probably find me. And yeah, I'm gonna hand it off.
Right. Oh, Jason, can you enable screen sharing?
Oh yeah, sure. Let me just make you co-host.
Okay.
All right, there you go.
Cool. All right, can everyone see this? All right, cool. So I'm Sachinda, and currently I'm an undergrad working on research with Professor Berg-Kirkpatrick. You might have had him if you've taken CSE 151A. And today I'm going to be talking a bit about how to teach computers how to read music, actually. So it's kind of like, in simple terms, it's kind of like OCR, so optical character recognition, but for music. So here's basically a rough outline of what I'll be talking about. So first, I'll be explaining what sheet music is. Then I'll be talking a little bit about what optical music recognition is and like what are its uses. And then I'll be going over what people have done in the past for OMR, and then talking about what people are doing now with the rise of deep learning pretty much, and my current research on OMR. So what is sheet music? So I'm sure many of you probably have never seen any music before, sheet music, but I think the easiest way to think of it is just imagine a paragraph of text. So something like this. This is just a paragraph from Wikipedia about music, and structurally, I feel like the most straightforward way to describe it is there's a bunch of different lines, and then on each line, there's a bunch of different words that are made up out of letters. And now if you look at sheet music, you'll notice the structure is actually pretty similar. So we have a bunch of lines, and then on each line, there are a bunch of different symbols. So except these symbols correspond to notes. And so here's a small sample of some sheet music. I can play it really quick. You might recognize it. So yeah, if you're a fan of Mario, you might recognize it. Anyways, so in terms of what makes up sheet music, so there's a bunch of symbols, like I said earlier. And so symbols over here on the left are, they basically deal with the style of the music, kind of, or for lack of better words. But for the purpose of this presentation, don't worry about these symbols on the left. For this presentation, all you need to know are notes. So all of these symbols here with these circles and then like these lines coming out of them, which are called stems, are notes. And each note in music has a pitch and a duration. So a pitch in music is just like how high or how low the note is. And a duration is pretty self-explanatory, is how long the note lasts for. And in terms of sheet music, the way to determine the pitch of a note is to look at where the note is respective to these 5 lines, 5 horizontal lines you see here. So for example, yeah, on this line where my cursor is, if you move across the screen left to right, everything at this position will correspond to like a certain note, or to the same note. And then for determining the duration of a note, you need to look at basically the stem over here, as well as the actual note head itself. So over here on the left, you see that it's like a hollow note, and that corresponds to a different duration. And in terms of these stems, over here, you can see that this stem has like 2 little lines at the top, and that basically means it has a different duration than the note over here, which has a stem with just a single line at the top. So what is optical music recognition, you might be wondering? So OMR is basically when you have some image of music and you want to be able to get a like machine readable encoding of it. So in terms of like what exactly machine readable encoding is, I think like a simple way to think of it is just like a list of every single symbol that you see in this image, this music sheet, the sheet music. Yeah, and just like in some sort of representation of every symbol. So a basic OMR system would be able to take in an image as shown above right here, and then it'll generate machine readable encoding, which consists of all of the symbols and notes that make up the music. And with that machine readable encoding, basically you can open it up in any sort of music editing program, and you can edit it right there. So now for some uses for OMR. Actually, like one of the first reasons I got interested in OMR, I think like back in high school when I used to play violin, sometimes I'd be practicing a song and I'd be like, this part looks really hard. I wonder what it's supposed to sound like. And then I'd always have to pull up YouTube, pull up a recording, and then scroll like all the way through the video and find like the exact location where someone's performing that part. But if you had OMR, you could literally just take out your phone, take a picture of the part that you're trying to figure out, and then you could just have your phone play that back for you right there. So I think that's one really cool application of it. Another application of OMR is I found this pretty prominent when I was back when I was in an orchestra in high school. So sometimes if you want to play just like music for fun with your friends, you might look up a certain song you like, but then, oh no, it's for flute. And then it turns out you all play like cello or something. But so normally you wouldn't really be able to do much, but if you had OMR, you could just take a picture of this music for flute, pull up your computer, and then open it up, and then you can basically transcribe that or transpose that to be playable on a cello in like without having to do much processing, because normally you'd have to basically manually enter all of the notes yourself, which is a very tedious process. So another use for OMR is more for like historical purposes. So there's I feel like a lot of classical music is pretty old and like it hasn't been digitized yet. So oftentimes all we have is just like an image of it, and this can make redistributing it pretty tough. Of course, there's probably copyright concerns about this, but it'd still be nice if we had like an easy way to digitize sheet music, because otherwise it requires people to essentially go through like some classical music and note by note enter it into some music software. And lastly, I think it's kind of futuristic, but like once OMR is really good, we could technically just scan a bunch of music sheets and then perform large-scale analysis on this music. And essentially, I'm not sure how many of you have seen like these AI models that are able to generate music nowadays. So basically, using OMR, we could basically get a bunch of sheet music digitized, and then we could have some AI model that is able to use all of that data to ultimately generate completely new sheet music from scratch. And I think that's a pretty cool application in the future. So traditionally for OMR, there was like this huge pipelined approach that was very messy, to put it nicely. So essentially start with some image like this. And then first you do like a bunch of pre-processing. In this case, what I've shown is basically you just binarize the data, which is converting every pixel to either black or white using some sort of threshold for the pixel value. And there also might be other pre-processing techniques such as like noise removal and stuff like that. And then after you do the pre-processing, you will go to this music object detection stage, which is basically in music, like I was saying, you have these 5 lines across that go horizontally across the page that determine that tell you what the pitch of a note is. And essentially, for most OMR systems back in the day, they essentially would have to do some sort of processing that removes these staff lines, because when they did have the staff lines in the image, they had a lot of trouble detecting like the music notes from within an image. So essentially, it would be like some really complex algorithm, computer vision algorithm, that extracts these lines for you, and then you're left with this image down here. And at that point, you're able to detect each of the music notes. And then the final stage is notation assembly, which is essentially so you've detected all these music notes, and now you need to determine like what they correspond to. So you'll make your prediction. In this step, you make your predictions of what note each box represents. And then you'll have to find out, using like some sort of heuristic algorithm, you will come up with a way to go from having these boxes with boxes associated with each note to an encoding like this shown below. So as you can see, that was a pretty complicated process for doing OMR. And before I get into the more modern machine learning approach to it that's being used a lot today, I want to just give a quick overview of supervised machine learning in case any of you aren't familiar. So essentially, all supervised machine learning is, at a super high level, is you give a computer a bunch of data with descriptions of the data, which are known as labels. So here you'll show a picture of a dog, have a label labeled as a dog, show a cat, have it labeled as a cat. And then the idea is, after you've shown the computer a bunch of data like this with the labels, it learns how to predict the label of an input image. So if you feed in an image after you've shown the computer a bunch of previous data, you'd hope that it outputs that this is a dog. So for applying machine learning for optical music recognition, there's probably like 2 main approaches that I've seen currently. So the first one being an object detection approach. So if you, back when I was talking about the traditional approach with the pipeline, where one stage of the pipeline was to do this object detection of the music notes. With the current deep learning capabilities, we're actually able to do like this object detection step, just like from the raw input image without having to do any pre-processing. So we can basically, looking at this image over here, we won't have to binarize it or remove any of the stabs. We can just immediately figure out, detect all of the objects in all of the music objects in the image. And this might seem like a good idea, but I'll explain a bit. In a second, I'll explain why this isn't actually such a feasible idea for OMR. And the alternative to that is, or the solution to this, is going to be an end-to-end system, which I'll be mentioning in a bit. So with the object detection approach to OMR, essentially what you do is you have some image like this, and then you'll feed it into a neural network, which is just, if you're not familiar with a neural network, just think of it as a black box, and it'll generate all of these little rectangles around each little symbol in the music. And so, going back to what I was saying about how this object detection approach isn't super feasible for OMR. So let me just, if I take away the underlying input image, all you're left with is, as you can see, a bunch of rectangles. And so that's essentially all that the computer is going to have. And with just this, you can see how it can get quite challenging to essentially rearrange this into a sequence of symbols that you can easily encode in a machine readable format, because there's going to be a lot of cases when the boxes are overlapping, like over here, and you're going to have to deal with a lot of ambiguities, trying to resolve a lot of ambiguities, resolving these bounding box collisions. So an alternative to this object detection approach to OMR is just a full-on end-to-end approach, where instead of trying to like detect all of the nodes and then put the nodes together in the appropriate sequence, you'll have a model that just generates the whole sequence right there. So what this would look like is you'll pass in this image into the neural network, and then the output of the neural network will straight up just be every single symbol that is in this image. So like clef, key signature, and then all of the nodes left to right. And with this kind of output, it's really straightforward to go to this machine readable encoding. So yeah, you can just write a really basic program that converts sequences like this into the desired encoding for OMR, and it's like a universal encoding for music. And yeah, now I'll go a bit into like how this end-to-end system works on a high level. So essentially you start with a window on the left of the image, and you slide it across the whole image. And at that point, you'll get something like this. So when you have a bunch of these little windows, and at each window, the neural network will output the symbol that it thinks is the most likely. So at the first window, it'll output clef. The second window, it'll output key signature. So on, and like, of course, you can see like there's some issues, or there's some challenges with windows being or like symbols being split between windows. But I don't want to go into the details of, I don't want to get into like the nitty-gritty, but there's ways to deal with it. And also, if you're familiar with neural networks, the architecture that this is using is like basically a CNN to extract the features, and then a bidirectional LSTM. So now I'm going to talk a bit about like the evaluation metrics. Oh wait, I just saw a question. Okay. Could you also do semantic / instance segmentation to avoid overlapping boxes? Yeah, I believe you could. You definitely could. Yeah, you definitely could do like some sort of like, I guess, higher level segmentation to avoid this like overlapping bounding box issue. And yeah, I haven't tried it myself, but it could definitely be a good approach. Okay, back to the evaluation metrics. So in OMR, it's kind of a newer field in terms of in terms of applied machine learning. So there's basically two metrics that have been becoming common, and the first one is sequence error rate, which it just represents the number of wrong sequences in like some data set. So when you're training an OMR system, you basically would be giving it a bunch of these little samples like this, and then looking at the prediction, and you train it by giving it samples like this along with the corresponding labels. And so one issue, I guess you can see with this metric, is that let's say our model is able to perfectly predict every symbol in the sequence, but then it misses one symbol, then it would technically be counted as wrong. So I feel like that's pretty unfair because it's like 20 other symbols that it got perfect and it just missed one. So it feels kind of bad just having to count that as an error. So instead, there is another metric called symbol error rate that is a lot more generous. I think it's a lot more fair too. So rather than measuring like if a sequence is completely correct, it basically looks at the number of wrong symbols. More specifically, it compares it looks at edit distance, if you're familiar with that. And yeah, so in this sample, you can see there's 3 notes and one note was predicted wrong and the other was in one note is wrong in this prediction. So the symbol error rate would just be 33%. And of course, like if you were trying to use sequence error rate, this would just be 100% error rate. So now I'm going to talk a bit about like my research focuses. So personally, I feel like the most interesting challenges within OMR is like complex music. So when you have multiple notes and melodies and voices that can happen at once. And I'll be showing some examples of that in a second. And the other area I've been interested in is generalizability. So as you know, there's a lot of different types of music in terms of like the style of it. So there can be typeset music, which is like this printed music that I've been showing. There can also be photographed music or handwritten music. And these all have a lot of very different properties. And I'll be going a bit deeper into this in a bit. So in terms of OMR for complex music, currently most OMR research is done on monophonic music, which is like what is shown here. Essentially, there's you can only have one note at a time. So if you look at the sequence, you only have to worry about one symbol at a time. There's never multiple notes stacked up at the same time. And with this, I'd say for typeset music like this, which is like just like typed music, models are able to perform really well. I'd say like 99% accuracy, which is symbol accuracy, which would correspond to maybe like 90% sequence accuracy, which is pretty solid. I feel like it's basically solved for that purpose. But for stuff like polyphonic music, which is when you can have multiple notes happening at the same time, as well as multiple rhythms. And what I mean by multiple rhythms is like, you can have 2 notes happening at the same time, and they also have different durations. So like over here, there's 2 notes happening at the same time, and the note on the bottom has a different duration from the note on the top. And that can also be like extra challenging for an OMR system to deal with. And currently, so with what I've been working on, here's an example of like something that the system I've developed can perfectly predict. And here's an example where the model struggles a lot. As you can see, like these, this sample has like a bunch of notes occurring at the same time, which makes it very challenging. And these red boxes show the spots where my system is not able to handle this, or is not able to predict the symbols correctly. And in terms of generalizability, so like I was saying, there's typeset music, which is the easiest. It's, as you can see, it's kind of like doing like character recognition, for example, on like printed or on like untyped data. Then like I say like the medium difficulty is scanned or photographed music. And in terms of making systems that can handle this, one approach is basically through this thing called data augmentation, which is when you have some image or like some data, let's say you have a bunch of typeset music, then you can perform some sort of operation on the typeset music to make it look more like photographed music. So if you're familiar with linear algebra, for example, to go from something like this typeset music to a scanned or photographed music, you could apply like an affine transformation to this typed music and also do some relighting effects. And then you'll have something that looks like this. But one of the most challenging types of music is handwritten music, which looks like this. And the main reason for this is because there's a bunch of variability, because obviously everyone has their own handwriting and styles of notating music even. So that can be a pain to deal with unless you have a bunch of data. That's also another challenge with handwritten music, is that there's not much data available. And with supervised machine learning, it's pretty reliant on having a lot as in like tens of thousands ideally of labeled data. So it's pretty challenging to develop a system for handwritten music that uses machine learning at least. So my idea for solving this issue of this lack of handwritten data is to essentially come up with a way to generate handwritten music from labeled typed music. And currently the results aren't very promising, but I feel like over time, it'll definitely be possible to generate something that looks more like the skull image over here. And yeah, so I think we're about out of time, but feel free to ask any questions if you have any. Thanks, everyone. All right, I'm going to go ahead and stop sharing then and hand it over to Jason for the last presentation.
Great. Thanks, Sachinda. Let me share my screen. Just 1 second. Okay. Let me move some windows over. Okay, great. So unfortunately, I can't share these slides, and it's for the same reason that I actually can't share our actual solution. But what I can say is that I'm going to present some really exciting results that show really significant improvement in a very interesting problem. And so to motivate what this problem is, by the way, special thanks to my advisor for just being an awesome advisor. Her name is Professor Lily Weng in the data science department. But again, to motivate this problem, and this is just the disclaimer that I just announced, basically we can't release our solution yet because we haven't released our manuscript yet. But once we release our manuscript on arXiv, then I would be happy to go over how we achieved our good, awesome results that you'll see. But this might not happen for at least, I don't know, end of spring, earliest end of summer, maybe. So hang tight. Maybe next year we'll do another one of these, and I'll be able to present my paper. But anyways, let's imagine a scenario. It's currently the future, all right? Some of you may get this reference. And you are chilling in some parking lot, whichever you identify as. And, you know, you're doing stuff on your laptop, maybe training deep learning models because that's really cool. And say you go for a walk, you leave your car, but it turns out that there's a really bad person in the car right next to you. And this really bad person is also really smart. And maybe they have an accomplice, right? And this really bad person is a hacker who has a lot of technical skills and know-hows and is able to hack into your futuristic autonomously driving car and mess around with the neural network that underlies the autonomous driving capabilities. So now your neural network is a little funny. Something's a little wrong with it. But Mr. Hacker Man or woman or person is very smart. So they're going to be very discreet about it. It's like you won't even be able to tell. But something is still wrong. And so you come back to your car, you take off, and you end up at an intersection. And the intersection shows a red light. And, you know, assuming this is far in the future, maybe your autopilot system is very, very advanced, super high performance. Basically, it's like a human driver, hopefully, in terms of being able to understand the road. You know, before Mr. Hacker person decided to mess with your neural nets, your car would say, "Oh yeah, that's a red light." But after Mr. Hacker person or Mrs. Hacker person messed with your neural net, now all of a sudden your car thinks that a red light is a green light. This is clearly very, very dangerous, right? If your self-driving car thinks that a stop sign means go, and you approach an intersection, your car is going to probably put you in a life-threatening situation, to put it lightly. We do not want this, right? And this might seem very futuristic, but it is a very real problem that exists today. And these kinds of hacks are called adversarial attacks. In the previous example I just showed you, the attack type is called a targeted adversarial attack. We can actually target a specific class, for example, green light, that the neural network should produce given some image. You can also have an untargeted attack where instead of green light, you would have something totally random like pedestrian or skateboard or camel or a dog, right? So there's different kinds of adversarial attacks. And this can happen whether or not the attacker has the ability to look inside your neural network and mess around with the weights. Or even, they don't even really need to mess around with the weights. They just need to look at the weights, the parameters of the neural network. It doesn't even, they can do it whether or not they can actually look at the neural network parameters. And you might be saying, well, hey, I mean, both of these images, they look like a red light, right? No human, no reasonable human would look at this image and tell me this is a green light, unless you're colorblind, which unfortunately then this is a very bad example. right? But hopefully the idea is still still pertinent for you colorblind people. No reasonable human would assuming they can see color, no reasonable human would make this kind of decision, right? And so you might blame the neural network, right? You might say, hey, this neural network is supposed to be 2077 level super duper neural network, superhuman performance, right? It's trained on millions and millions, by that decade, probably billions and trillions of examples. It's supposed to have like 99.99% accuracy or whatever. What went wrong, right? Clearly something non-human is happening here. Something non-human and something dangerous. And so let's talk about this reasonable expectations for AI, both within that example and in general. So obviously our reasonable expectation is that, by the way, before I start that point, I'm going to tell you exactly what the hacker person did. All the hacker person did was take the image and change a few pixels, fuzz around some pixels here and there in such a way that you as a person would not be able to perceive the changes. So there's a question, did the hacker occur during training the neural network, or does the car have a pre-trained neural network which has been sabotaged? It's the second. So they don't even necessarily have to change any of the trained weights. They can actually just pass in a special image and get this kind of result. So this is an attack on the input, to be precise, right? And again, there are some pixels that may be a little fudged up. Maybe they increased the value of this blue pixel by like 0.01. You wouldn't be able to tell, and you also wouldn't really care, right? That doesn't change the fact that you still see a red light here. But if you do this, it turns out, in a very clever way, you can actually fool neural networks that aren't prepared for this kind of attack. And that's a very big problem. It's a very big problem because for a few reasons that we'll talk about. Right, so our reasonable expectation is that changing a few pixels in that manner shouldn't change, at least that drastically, what your output is for your neural network. Another reasonable expectation, just another example, is if you're not on the road, but maybe you have a personal assistant that has to, like in the future, that is a robot personal assistant that has a computer vision system on board. Maybe they identify a house cat. And maybe the hacker person also hacks into your personal assistant, right? Maybe they're taking care of, maybe the personal assistant is taking care of your grandmother or your grandfather, right? That's another place where things can get very dangerous, right? And say this exact same thing happens, they run the attack on the input. And, if you look at these two cats, it's reasonable to say, hey, those are both cats. Actually, those are both the same cats, you would say. But again, we can have an attack that produces very different outputs for these two. You could say, oh, that other cat's a dog, or that other cat's a sandwich, right? And then, hopefully your personal assistant would not make any harsh, rash, unfortunate decisions based on that unfortunate outcome. Another example, not necessarily classification, but in terms of explaining how we get those classifications, right? It's actually interpreting what goes on in a model. We would also have a reasonable expectation that if you fudge up some of those pixels, for example, in our red light example, and say both were classified as red light, right? Then the explanation or how that output was produced for the normal image shouldn't be different from the explanation of how red light output was produced for the slightly fudged up image, right? These are reasonable things that we would expect as humans. So one important point I want to make, and this is in the title of my talk, is that these reasonable expectations are human biased. And so what that means is that these are reasonable from our perspective, right? They might not be reasonable from a machine's perspective. My argument is that, well, they should be, right? They should be, these expectations should be human biased. That's okay to some extent. And the reason why is because, or reason why I think this is the case is because, well, they're designed by humans. They're going to be for humans. They're going to interact with humans. It's reasonable to expect them. We want them to behave in human-like ways. And so it's reasonable to have human bias expectations for AI. Having these reasonable expectations leads to greater trust if we don't have any surprises. And it's especially important, as our examples have shown, in critical applications such as autonomous driving or healthcare or criminal justice or the many other scenarios, personal assistant taking care of a grandmother or whatever, right? And I say to some extent for my argument because in some cases, it seems like AI makes a decision that does not seem reasonable from a human perspective, but ends up actually being very, very smart. AlphaGo beating the world champion in Go is an example of that. And so in some scenarios, perhaps human bias expectations should not be limiting to the capabilities of AI. But you can also think, well, is it possible for an AI to make a decision that ends up actually being a very, very smart and safe option, but appears unreasonable in the moment, right? Maybe you have a robot that is very capable, very mobile, think Boston Dynamics level, that saves some person in distress, but the way they do it is so unconventional, but ends up being accidentally genius, at least from our perspective. And so maybe we need a balance, right? Maybe we need a balance of things that we can expect as humans. Definitely in scenarios where like we have autonomous driving or vision, we want that to be human biased. In other scenarios like games like AlphaGo, then maybe we could just let the machines run free. And so the cyberpunk example I gave you, how can we actually meet these reasonable expectations, right? How can we actually ensure that no hacker person can mess with our model in a way that leads to this problem? The solution is something called robustness, or to train your model to be robust to these kinds of adversarial attacks. And there's a few ways that you can achieve classification robustness, right? For example, if you took all the possible images where you fuzzed up some of the pixels and you just added those to your training set and then retrain your model, then your model could hopefully learn to not make those silly mistakes. Another way is to actually optimize for robustness during training. And you don't necessarily have to add in all those perturbations like in adversarial training. you just have to define a special term in your loss function. And I give an example down here. This is work out of DeepMind. They produced a method called IDP for short, or interval bound propagation. And your loss function is basically this, and just your average, your normal loss function for performance, for correctness, right? Plus some additional term that has to do with robustness. That's basically the idea. And the third way is just have a model that's inherently robust, right? So by construction, your model is just robust to these kinds of things. There's all these different ways that you can meet these expectations for classification robustness. So our research is related to robustness, but we're not looking at robustness of classification output. We're actually looking at robustness of interpretability. And this actually goes on to the message I sent at the end of Stone's presentation about saliency maps. And so the image you see here is a diagram containing some input images in the far left column and a whole bunch of saliency maps. And so saliency maps, all they are these sort of heat maps that roughly tell you where the model is looking when it makes some sort of prediction. You can think of it as loosely explaining how the model arrived at its prediction. And obviously this is super important, right, to understand, hopefully, for example, when your model messes up, this could serve as a method to debug what happened, right? You also want to, it would also help you gain trust, or others gain trust in your model. If they knew, if they could say, hey, model, how did you arrive at this conclusion? If the model, all the model said was, sorry, I can't tell you. You know, it's very hard to trust a model that does that, right? So that's why we need interpretability. Again, you can either get interpretability through saliency maps by doing this. Basically, given an input image and a neural network, you pass it through the neural network, and then that produces some output. Typically, we're only concerned about the class that's given highest probability in the output. And then we look at that output neuron, and then we say, okay, explain how you got that. And that's how we produce these things, right? Through different methods, right? But the overall idea is the same. Like robustness for classification output, you could also have inherently interpretable models. So by construction, again, a model is inherently interpretable. For example, Stone actually mentioned one, which was the decision tree, right? It's very easy to interpret. And in fact, people have extended the decision tree to combine them with neural networks. And this is called the neural-backed decision tree. And this was released, I think, 1 or 2 years ago. It's actually very recent. There's another model, if you're interested, called the self-explaining neural network that is supposed to be also inherently interpretable, but in a totally different design from a decision tree. It's not a decision tree at all. It's just, like the name implies, a neural network, right? So anyways, there's different ways that you can get interpretability. But that's not the problem we're concerned about. The problem with interpretability is when we ask the question, are they reliable? Are they reliable in the same way that we saw in our cyberpunk example, where we had that reasonable expectation that adding some pixels, fuzzing up a bunch of pixels in your image shouldn't lead to drastically different output. For interpretability methods, the parallel here is that adding some pixels or adding some perturbations to your image should not change, for example, the saliency map that much, right? Especially if it led to the same classification output, right? So, for example, here is from a paper that looks at this issue, and if if you're watching the video, I guess you can type this URL by hand. Basically, we look at the original image, and then we perturb it a bit. And then in the second row, we look at the saliency map, just like we saw in the previous slide. And clearly, by perturbing this image, we get saliency maps that, I mean, the overall shape is the same, but you're getting these pixels. For example, here, you get this pixel that is marked as very important. Dark red, by the way, means very important. That did not show up in the original saliency map. And so what this means is that you can manipulate the saliency maps as well, just like you could manipulate the classification output by perturbing some input images. And hence, we have another grave safety problem, right? Imagine that your neural network not only was not robust to classification output adversarial attacks, but also not robust to methods that hopefully try to explain what went wrong in the first place, right? It's like a 2-for-1 in the worst possible way, right? So an important thing that we need to establish is, how do we actually measure robustness, right? Especially of interpretability. How do we quantitatively measure this, right? Do we have to, for example, look at all possible perturbations of an image and see how many our model gets right? That would probably take forever. And it would take forever, and people do not do this in practice, right? Instead, what some people do in practice, for example, one thing that my advisor worked on, Lily Weng, is this certification called Corgi. Corgi, basically, the certification is this theorem, meaning we can provably show that our model is robust without having to evaluate, potentially many perturbed variants of an image, right? And because we have a proof, no one can claim that, oh no, your model, what if it wasn't robust on one image, right? Well, no one can claim that because we have a proof, right? And that's the great thing about things like Corgi, right? Like certification methods like Corgi. And all Corgi says is that, hey, if you look at the top, k pixels, where k is some integer, of your saliency map, let's certify that those k pixels will remain the top k pixels in your saliency map for a perturbed image, right? So for example, like maybe the 10 darkest dots in the original saliency method should still be the 10 darkest dots. Maybe the values changed a bit, but they should still be the top 10 in terms of the darkness value or the importance value, right? And also note that order doesn't matter. As long as the set of pixel indices remains the same, it doesn't matter, that one pixel became like swap places with another in terms of how important it was. We just want to certify that the top k are still the top k, no matter what the ordering became. So if we can guarantee that the top k pixels didn't change or won't change within what is defined as a perturbation radius. So radius, you can think of, you have maybe like your normal image, and then you have your perturbed image, and really these two are just vectors, and there's some distance between the vectors. Say that distance is delta, right? We can define a maximum delta for which any image, a distance less than or equal to that maximum delta, satisfies the certification. In other words, any image, some delta or less distance away from our original image won't change the top K pixels of your CAM map. CAM, by the way, being the method of the saliency method used here in this certification. So in other words, this certifies interpretability robustness, right? And then what we can do is, we can evaluate the certification at some delta, right, at some radius. And then either we get, yes or no, can we certify it, yes or no, for that particular radius. And then all we can do is, so what we're interested in is, what is the highest delta that we can guarantee, right? We want our radius to be as big as possible because we want to encompass as many possible perturbations to guarantee in our certification. And so all we do is just binary search for the largest such radius, right? We look at, for example, in the range 0 to 1, we start at 0.5. We say, can I certify? If yes, then your new range is 0.5 to 1, right? We're trying to move up our search for the radius. If no, then our range is now 0 to 0.5, right? We want to search for a smaller radius to certify. And note that just gives a lower bound on the robustness. This might not mean much to you right now unless you read the paper. But basically all it means is that it's an estimation, but it's still a guarantee. So it's not exact. It could be that, but it's only saying that your model can only do better in reality, right? Like we know for a fact this is a baseline, is all we're saying, right? Maybe the model is even more robust than we certified. That's great. We get, extra robustness. But we at least know it's this whatever radius that Corgi specifies. And so here's a diagram from Corgi paper. And it basically shows, you have your original images, you have your perturbed images. These basically look the same. And you'll note that, in the perturbed images, the top K pixels are different, obviously, especially in this scenario, right? For different perturbation radiuses. And Corgi guarantees that all of them are the same. This is what Corgi guarantees, that they're the same. This is what we want to avoid. And so obviously our problem is, well, we can certify, right? We can evaluate, we can answer the question, how robust is my model as is, right, to adversarial attacks on interpretability? But how can we actually improve, right? How can we say, okay, it's this as a baseline, well, let's make it better, right? Maybe it's doing poorly, let's improve it, right? Can we even do this in a way where, like Corgi, we provide some sort of theoretically grounded means? And this isn't just something that, by happen chance, it improved the Corgi radius on this one, limited set of experiments, right? And we're not even sure why, right? No, we want to actually, theoretically, mathematically ground our work here. And so really quickly, the answer initially seems to be yes. What we found is that we can actually improve the Corgi radius by a factor of at least 35 times over a normal model that is not specially modified using our solution that, again, I unfortunately cannot go into. We still have to do more experiments, definitely, but this is extremely promising, right? This demonstrates that it is possible to improve in a theoretical manner our interpretability robustness. But the trade-off here, you might be wondering, wow, that sounds very great, but what's the catch? The catch is that, at least initially what we discovered, is that you'll have a trade-off with accuracy. So you'll get a model that's more robust, but it's not able to classify as many images correctly. And so here's a table that demonstrates this. Nominal accuracy is just your normal accuracy. And here's the average radius that is able to certify. We ran this over all 10,000 images in MNIST. And here you see the 35 times improvement of our solution versus a normal model. Here is just the model that's robust to classification output, a taxon classification output. For example, IDP that I mentioned earlier. This leads to a 10 times improvement, and we were able to improve by more than 3 times over that. And so this basically just communicates the same information. We're able to improve the radius on average. As well as this. So if you look at the robust classification model, that improved the radius for 90% of images. But in our solution, we were able to improve it for 97% of images on the 10,000 test images in MNIST, right? So you can calculate how much that is in terms of the number of images. So not only were we able to, on average, improve how large the radius was, we were able to do so for more images through our solution. And this is the last slide. I know I'm a bit over time, but qualitatively, here's what our saliency methods saliency maps look like, right? First column for each image is standard model. Second column is our model that's robust to classification output. Third model is our solution. So you'll see that qualitatively, it seems like it's giving, so red is very, very positive, blue is very negative. Qualitatively, it seems like our CAM maps have more importance, they give more red pixels, basically. Sometimes this looks a little bit too much, so we'll have to do some analysis on what happens there. But that's basically my presentation. Yeah, I'd be happy to take any questions. Nearest 2021. We'll see. Probably not, but worth a shot, I think. Thanks. Thanks, John. Okay, if there are no more questions, I'm going to stop sharing. Actually, I'll just switch to this part. So at this point, we do have a general Q&A, but technically the event is over. Feel free to ask us, the presenters that are still here, any questions about anything related to research. If there are no more questions, then we could just end the event. But yeah, we'll open up to questions now. So this looks like a question for my research. So I know that in robustness resiliency issues in multi-agent systems, so okay, I'm assuming you're talking about reinforcement learning. So the common strategy for robustness is to ignore the strongest incoming beliefs. Okay, I'm not familiar with that method. Would something similar be possible with saliency maps of ignoring the top K most salient pixels? I think the first question I would ask is, why would you ignore the most important parts of your saliency map, right?
Yeah, I guess
Hold on, my speaker's on mute. Yeah, so
do you want me to follow up on the question?
Yeah, sure.
Give more detail. Okay, so what I'm coming by multi-agent system, I'm actually referring to a kind of very specific one which is if there's, let's say, agents are measuring, like testing some hypotheses, and they're sharing kind of their beliefs or knowledge. Like each agent has a partial knowledge of the environment. Altogether, a network of agents is supposed to have complete knowledge of the environment, and you kind of need everyone to come to a consensus on what's the true state. And the question there is like, well, what happens if in this network you have some malicious adversarial agents who distribute false information or like just misleading information or any sort of adversarial attack you want? It could be even like a just Byzantine problem attack. And so one of the kind of heuristic solutions that's been approached is that when an agent's using incoming beliefs to update their current beliefs, so like another agent tells them that this is kind of my belief about the state of the world, and they have some neighboring agents, like a group of neighboring agents. What they do is that whatever is kind of this most extreme belief, like either it's this hypothesis about the world is very true or this hypothesis is very false, for example, something like I'm simplifying a bit, but it would kind of throw those out. And so this would make convergence to like a consensus slower in a sense, especially to the true one, but it would prevent kind of being exposed to these highly kind of swaying beliefs. I guess I've probably explained it a bit too quickly and a bit too simplified, but I was thinking is that in terms of these adversarial attacks onto images, it seems that one of the things that throws classification off a lot is that you have some new pixels that are incredibly salient, and those make the model diverge in how it perceives the image. And if you instead ignored, however, like maybe K, like, I don't know, 3, 5 most salient pixels, it might harm your classification ability a lot. I'm not sure. I don't know how relevant it is, but at the same time, it could make you a lot more robust to like very small changes in terms of like pixels.
Yeah, so you would somehow need to isolate those salient pixels. You'd also need to know beforehand, like a priori, before you run through your neural network, which pixels are the most salient in the first place. But with these methods, the saliency map methods that I talked about, you don't know that until after you've run through it neural network. So it's sort of like a chicken and the egg problem.
Oh, I see. Okay, so saliency maps aren't like done at the same time, let's say, as the neural network is.
Yeah, you have to, at least with these methods, you have to run it through once, and then you can say, okay, let's do like this post-mortem on what happened.
Okay, I see. Then I think I misunderstood saliency maps. I was under the impression that it was like the neural network was kind of almost using these saliency maps in order to.
I see. Yeah, that's not what happened in that.
Okay, that makes sense. Then yeah, thank you.
For sure. Okay, any more questions? Okay, here's a question, and I guess Sachinda, maybe you want to talk about this first. How did you guys start doing these awesome research?
Sure, I'll go first, I guess. So my sophomore year, my second year, going into my third year, I knew I wanted to do some kind of research, to at least try it out, because I wasn't really sure if I wanted to try to go down the research path or just go like straight to industry right after finishing my undergrad and maybe doing like a master's or something. So then I decided I wanted to try research, and then I was talking to Jason. He'd also been working on research for, I think, the ESRP, I forgot. Yeah, ESRP program at UCSD. And he mentioned that the professor he was working with, Professor Berg-Kirkpatrick, happened to do like some music related research. And that's really interesting to me because music's a pretty big part of my life, and yeah. So I basically I sent him an email sometime in like last spring, and didn't get anything back from it at first, but then I followed up a few times and eventually he got to it and he was like, yeah, I'm down to work with you for the honors research program, the CSE one. And yeah, that's basically how it started. So I guess my advice for you, okay, yeah, if you want to do the CSE honors program research thing, just like, if you think of some idea that you're passionate about, just feel free to reach out to any faculty that you think might be interested in doing something related to what you're interested in. And yeah, shoot them an email and yeah, it should work out. There's a lot of faculty. And I feel like professors are generally pretty open to working with undergrads, even as long as you're enthusiastic about the research. So yeah.
Yeah, so as Sachinda mentioned, I first got involved in research through this program called ERSB. It's in the CSE department. It is spearheaded by Christine Alvarado. She's really awesome, by the way. Shout out to her. Basically, if you're a rising second year, yeah, so if you're currently a first year, rising second year, or your incoming transfer, then you can apply, or they're targeting those people. But if you're not, I think you can also still like make a note and maybe they'll make an exception. But programs like that, programs like ERSP, which kind of are structured and they like pair you with a professor, those are a very natural way to get involved in research. And then from there, you sort of, start to cold email if you want to jump to another lab or whatever you want. The research I'm doing right now, what I did was I did do a lot of cold emailing. Well, not too much. I cold emailed like 4 professors. Basically, I tried to present in my email, hey, here's something I'm interested in working on. Here's a sneak peek at an idea. Let's meet to chat about it if you have time and if you're interested. That's some replies, and basically from there, now I do research with Lily Weng. I would also add on, I mean, Sachinda gave some pretty good advice. I would also add on, definitely be diligent and show that you can sort of take charge of your research and that you can show initiative and do some literature review on your own and really know a bit about the area before you meet the professor, stuff like that. Showing that you can really take charge of your project and that it's not going to be like a drag or anything. Hopefully not. But yeah, that would be my advice. Yeah, no problem. Any more questions?
For Sachinda, how much have you explored of the field of music generation, or have you been mostly just doing music breaking up the OMR?
I've actually not explored music generation at all yet, but I think once I finish working on OMR stuff, that'll definitely be something I'll look at.
Okay, yeah, I mean that area seems very interesting. I'm very curious as to how AI would, for example, go from recognize. I mean, something like jazz, for example, would be very, I think, difficult for an AI to generate, as opposed to maybe classical music stuff. But
true, I feel like as long as you have the data for it, in theory, it could be possible to do some more jazzier generation.
Yeah, I don't know. Maybe you'll find some patterns, but I don't know. It seems like there's, I mean, jazz, as far as I know, is not really played in a sheet music style. There's no kind of explicit format or rules for how it should be done.
Sure. I know, I guess one possible approach to that would be so there's some tools out there that are available for transcription and stuff.
Mm-hmm.
So in theory, you could use those transcription tools on like jazz recordings, and then basically those will give you like, I'm not sure if you're familiar with like the MIDI data format.
Okay, yeah, I've heard of it. Yeah.
Yeah, so basically just like music notes. It's the format for representing music notes and their timings. And yeah, I feel like that could be a decent way to gather a bunch of jazz music data, and then I'm sure there's definitely models out there that people have been using for music generation, and I feel like you could probably apply that to that data as well. I don't see why not, but yeah, it'd be interesting to see like how it sounds in the end, because there's so much like variability.
Yeah, that's true. Also, is it easier to convert recordings into like say sheet music versus sheet music into like recordings? So like if you have a picture of sheet music, and convert that into what it would sound like, as opposed to taking what it sounds like and converting it to sheet music.
I think you're going from what it sounds like, at least for piano music. I'm not sure about like general music, like transcribing like a pop song or something like that. But at least for piano music, I know like my advisor actually, he's done some work on piano transcription, and I feel like he was showing us some demos where I think it was actually an ACM presentation, actually, if you want to check that out at some point, where he was basically on the spot transcribing piano recordings to MIDI. So it's not like sheet music. So I guess it's a bit different, because with sheet music, it's all about like the timing and stuff being exact. Whereas with performances and like audio recordings, there's obviously going to be like mistimed notes and maybe missed notes that is going to be difficult for a computer to basically like disambiguate.
Okay.
So yeah, I feel like going from sheet music to like audio could definitely be pretty challenging, because that is basically dependent on like the OMR capability. Although I guess like there's this one representation I've seen a bit called of sheet music called like a what was it? I can't remember the name exactly, but it basically was a representation where, so you'd taken some sheet music and then you would approximate all of the notes with like these like little squares, and that was supposed, and you could possibly use like something like that to go from that approximation to audio. And I feel like there'd definitely be mistakes because it's like an approximation, but I think in terms of robustness, it would work out better, because it's a more like algorithmic approach, I feel like.
Yeah. Okay. Yeah, thank you.
Yeah, no problem.
And thank you, Jason, for organizing the event. It's pretty cool.
Yeah, no problem. It was a pleasure, and yeah, I hope we could do more of these, by the way, in future quarters. Hopefully also when things go back to in person. That'd be great to see all these presentations live.
Yeah, oh, that's true, that's true. Okay, yeah, thank you.
Yeah, no problem.
Cool.
Yeah.
Yep, thanks for organizing this. It was awesome.
Yeah, for sure.
All right, I'll see you, dude.